12 men, 41 minutes, one engine that was never supposed to be there, and an entire racing career on the line with every single bolt they turned. Picture this. You're standing in a NASCAR garage in 1968. The doors shut, the lights are low, and 12 mechanics are moving around the stock car like surgeons performing an organ transplant. Except the patient is a 3,000-pound race car, the organ is a 427 cubic inch big block, and the operating room is a concrete garage bay that smells like gasoline and sweat. They have less than an hour to pull out a perfectly legal 350 engine and replace it with a monster that is not supposed to exist. If they succeed, their driver gains 120 horsepower and a near guaranteed trip to victory lane. If they fail, if one inspector walks by, if one bolt strips, if one hose leaks, it is not just a disqualification, it is a lifetime ban, names erased from records, careers destroyed, reputations gone. This is legacy motoring, and I spend way too much time thinking about the insane lengths racing teams went to in order to cheat the system. If you're someone who loves untold stories from the golden age of motorsport and the mechanical brilliance behind history's most audacious rule-breaking, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, here's the thing. When most people think about cheating in racing, they picture someone adding a little nitrous, maybe running slightly oversized tires, small stuff that gives you a marginal edge. What happened in the late 1960s was not marginal. It was a full-blown covert operation that would have made the CIA proud. Teams were swapping entire engines behind closed garage doors, transforming also-rans into dominant winners. And they were doing it with nothing but hand tools, brute strength, and the kind of nerve that borders on clinical insanity. To understand why anyone would risk absolutely everything on such a gamble, you need to understand what NASCAR looked like in 1967 and 68. The sport was at a crossroads. Speeds were climbing every season. Fatal accidents were becoming disturbingly common. Fans were filling grandstands, television contracts were growing, and the sanctioning body was under enormous pressure to slow things down before the next tragedy. Their solution was displacement limits. The rule was straightforward on paper. 358 cubic inches maximum for standard production engines. If you wanted to run one of the special homologation motors, like the Chrysler Hemi or the Ford Boss 429, you could go up to 430 cubic inches, but you carried weight penalties that were supposed to offset the power advantage. Look, in theory, this made sense. Cap the engine size, reduce power, reduce speed, save lives. But here's what most people do not realize. These rules did not level the playing field. They tilted it in a completely new direction. A well-prepared 350 with the best cylinder heads, the most aggressive cam timing, and meticulous blueprinting might make 475 horsepower on its absolute best day. That's solid, that's respectable. But a 427 with the same level of preparation? You're looking at 590, maybe 600 horsepower. That's not a 10% advantage, that's a 25% advantage. At a track like Daytona, where aerodynamics and raw power determine everything, that gap translated to roughly 8 miles per hour on the banking. 8 miles per hour does not sound like much until you realize that it's the difference between leading the draft and watching the entire field vanish in your mirrors. It's the difference between a trophy and a footnote. Now, you might be thinking, well, the inspectors would catch that immediately. And you would be right to think that, except for one critical detail. The inspection process in 1968 was, let us say, primitive by modern standards. There were no computerized databases, no digital seals with encrypted codes, no laser measurement systems. Inspectors used measuring tapes, visual assessments, and experience. They would measure bore and stroke to calculate displacement, check carburetor sizing, look for obvious illegal modifications. And once your car passed, you received a sticker on your windshield and you were cleared to race. The inspection area closed. Teams went back to their garages, and what happened behind those closed garage doors was between a team and their conscience. This is where it gets really interesting, because one man looked at that gap between inspection and race time and saw not a risk, but an opportunity. His name was Herb Nab, and he was Junior Johnson's crew chief. Herb was not your average wrench turner. This was a man whose education in engines started during the moonshining era, when building a car fast enough to outrun federal agents on twisting mountain roads was not a hobby but a survival skill. The bootleggers of Wilkes County, North Carolina were the original racing engineers. They lightened cars, modified suspensions, and built engines that could scream through the Appalachian darkness at speeds that would terrify a professional driver today. Herb grew up in that world. He could listen to an engine and tell you which cylinder was slightly lean. He could feel a vibration through the steering column and diagnose a bearing that was 0.002 inches out of spec. He understood engines the way a painter understands light, not just technically, but instinctively. In 1967, Herb had helped Junior Johnson win 13 races while supposedly running inferior equipment. Competitors scratched their heads. Junior's car should not have been that fast. The numbers did not add up. But nobody could prove anything, and in racing, suspicion without evidence is just jealousy with a different name. By late '67, Herb had conceived a plan that was equal parts genius and madness. The idea was deceptively simple. Build 2 engines, one legal, one illegal. Pass inspection with the legal one. Swap in the illegal one before the race. Win. Swap back if necessary. Repeat. Simple to say, nearly impossible to execute. But Herb Nab was not a man who was intimidated by impossible. The engineering challenge was not just building a monster motor. Any competent engine builder in 1968 could assemble a 427 that made serious power if the rulebook was not a concern. The real challenge was creating 2 completely different engines that were mechanically interchangeable in under an hour, using only hand tools. Think about what that actually means for a moment. Every mounting point had to be identical. Every accessory bracket had to bolt up in the exact same location. The bell housing pattern, the starter position, the alternator mount, the water pump configuration, even the height of the distributor. Everything had to match perfectly between a small block and a big block, 2 engine families that were never designed to be compatible. Herb spent the winter of '67 into '68 essentially reverse engineering both motors simultaneously. He fabricated custom engine mounts that could accept either block. He designed adapter plates that made the transmission think it was always talking to the same engine. The cooling system was perhaps the most brilliant piece of the puzzle. Instead of conventional hose clamps that require tools and time, he sourced military-spec dry brake connectors, the same type used on fighter jets for aerial refueling. Push together, they seal. Pull apart, they close. No drips, no mess, no time wasted. The fuel system got similar treatment. Quick disconnect AN fittings that aviation mechanics use. 1/4 turn and the line separates cleanly. But here's where Herb showed he was not just a mechanic, but an actual systems engineer. The electrical system was completely modular. Every wire that went to the engine, ignition, alternator, temperature sensors, oil pressure, all of it terminated at 2 massive multi-pin connectors mounted on the firewall. These were not off-the-shelf parts. Herb had them custom-made by a military contractor who supplied wiring harnesses for tanks. 24 pins each, color-coded, teed so they could only connect one way. During the swap, one mechanic could disconnect both harnesses in under 30 seconds. Reconnection was just as fast, and because they were keyed, there was 0 chance of crossing wires and frying something. The exhaust system was a work of art in its own right. Headers in 1968 were typically one-piece units welded to collector flanges. Removing them meant unbolting 8 or more fasteners per side while lying on your back in a cramped garage bay. Herb built his headers in 3 sections. The primaries attached to the heads with conventional flanges, but instead of welding the collectors, he used slip joints with spring-loaded clamps borrowed from industrial exhaust systems. Loosen 2 clamps per side, slide the sections apart, done. During installation, the sections slid together, the clamps tightened, and you had a sealed exhaust in under 2 minutes. Now you might be thinking, okay, smart fittings and connectors, but what about the actual mechanical work? Unbolting a transmission, lifting an engine, those are not quick operations. And you would be absolutely right, which is why Herb pre-staged every single fastener. This is the detail that separates amateurs from professionals. Every bolt that held the engine in place was brought to its exact torque specification, then backed off precisely one full turn. Not a quarter turn, not 3/4, exactly one complete rotation. Why does this matter? Because during installation, every mechanic knew that every bolt needed exactly one turn to reach proper torque. No guessing, no checking with a torque wrench, just one smooth rotation and move to the next one. The transmission connection was just 4 bolts, but those 4 bolts had to align with the bell housing while the engine was suspended in midair. Herb machined guide pins that inserted into 2 of the bolt holes. As the engine lowered into position, these pins guaranteed perfect alignment. Once the engine was seated, the pins came out, bolts went in, 1 turn each, done. The whole transmission connection took under 90 seconds. The lifting system itself was custom fabricated. Herb designed the spreader bar with 4 attachment points that distributed the engine's weight evenly. The lift points were machined into the cylinder heads at the factory, but Herb added reinforced inserts to handle the stress of rapid removal and installation. The lift itself was not some fancy hydraulic unit. It was a manual chain hoist mounted to a rolling gantry that could be positioned over the engine bay. Low-tech but reliable. No hydraulics to leak, no pumps to fail, just mechanical advantage and muscle. Here is what most people do not realize about the practice sessions. Herb did not just run his guys through the swap a few times and call it good. He treated it like a military drill. The team practiced in an abandoned tobacco warehouse outside Charlotte, working under conditions that simulated race day pressure. Lights kept dim to mimic garage lighting, a stopwatch running constantly. And Herb introduced random failures. Halfway through a swap, he would announce that a connector was jammed, or a bolt was cross-threaded, or the hoist was stuck. The crew had to adapt in real time, finding workarounds without adding time to the clock. This was not just about speed. It was about grace under pressure when your career was on the line. The first practice runs were disasters. 2 hours, 17 minutes, tools dropped, connections made in the wrong sequence, coolant spilled everywhere. But Herb was relentless. He debriefed every session like a football coach reviewing game film. Each mechanic had one specific job. The guy who disconnected the battery did only that, then moved immediately to draining coolant. The guy who handled electrical connectors touched nothing else. No overlap, no confusion, just a choreographed sequence that became muscle memory. After a month, they were down to 52 minutes. After 2 months, 41 minutes flat. And that included cleanup, making sure there was no evidence of the swap. No coolant puddles, no misplaced tools, nothing that would make an official curious. The legal engine, the one that would pass inspection, was built to the absolute letter of the rules. 350 cubic inches, forged internals because Herb was not going to risk a failure even in the decoy motor, aluminum heads that were legal but expensive, a cam profile that was aggressive but within specifications. This engine made about 470 horsepower, which was genuinely competitive. If the swap had never happened, Junior could have won races with this motor. It was not a throwaway, it was a legitimate race engine. The illegal engine, though, that was something else entirely. 427 cubic inches of pure, unregulated fury. The block itself was a rare casting, high nickel content, originally designed for marine applications where saltwater corrosion was a concern. But the real reason Herb sourced these blocks was that the nickel alloy could handle cylinder pressures that would crack a standard block. And he needed that capability because this engine was running 13-to-1 compression. For context, most street cars of that era ran around 9-to-1. Race engines might push 11-to-1. 13-to-1 was bordering on suicidal. It required racing fuel, the 103 octane stuff that smelled like a chemistry lab and cost more per gallon than most people made in an hour. The crankshaft was forged from 5140 steel, a material used in aircraft landing gear. Then it was cross-drilled, a process where holes are bored through the crank journals to improve oil flow to the bearings. This was not common in 1968. Most production cranks relied on simple oil passages. Cross-drilling was expensive and time-consuming, but it allowed the engine to survive at RPMs that would grenade a standard crank. Herb also had the crank knife-edged, meaning the counterweights were machined to sharp edges to reduce air resistance as they spun through the crankcase. At 7,000 RPM, windage, the drag from the crank pushing through oil, mist, and air, can rob 20 horsepower. Knife edging reclaimed most of that. The connecting rods were Carrillo forgings, each one costing $200 in 1968 money. That is over $1,600 per rod in today's currency. For comparison, you could buy an entire running car for less than a set of these rods, but they were bulletproof. Carrillos were used in top fuel dragsters, Can-Am sports cars, Indianapolis roadsters, anywhere that engine failures were not just disappointing, but potentially fatal. The pistons were custom-forged units with dome profiles designed to create the insane compression ratio, while still clearing the valves at maximum lift. This is a tricky engineering balance. Too much dome and you shrink the combustion chamber so much that the valves smack into the piston at high RPM. Not enough dome and you do not get the compression you need. Herb worked with a piston manufacturer for weeks, going through multiple prototypes, measuring clearances with feeler gauges and modeling clay to make sure everything worked. The camshaft was ground by Ed Winfield himself, one of the legendary cam grinders of the era. The specs were absurd: 740 thousandths of an inch intake lift, 688 thousandths exhaust lift. Duration was 318 degrees at 50 thousandths lift. To put that in perspective, a modern street performance cam might run 480 thousandths lift and 220 degrees duration. This cam had overlap, the period when both intake and exhaust valves are open simultaneously, that was so extreme the engine would barely idle below 3,000 RPM. It coughed, it sputtered, it shook the whole car like it was angry. But above 4,000 RPM, it was like somebody flipped a switch. The engine went from grumpy to ferocious in half a heartbeat. The cylinder heads were prototype castings that Chevrolet had developed for their Can-Am racing program, but never released to the public. How Herb acquired them is a story nobody will confirm, but the rumor is that a Chevrolet engineer who was friendly to the NASCAR teams mysteriously lost a crate during shipping and it ended up in Herb's shop. The ports were enormous, 230 cubic centimeters for the intakes, nearly double what a production head flowed. The valves were stainless steel, 2.19 inches for intake, 1.72 for exhaust, with titanium retainers that cost more than most people's monthly rent. The intake manifold was a tunnel ram design, which means it's that tall enough that Herb had to modify the hood with a subtle bulge to clear it. Two Holley 660 CFM carburetors sat on top, each one capable of flowing enough air to feed a big block on its own. Together, at wide open throttle, they can move over 1,400 cubic feet of air per minute. A typical street engine uses maybe 600. This setup was so oversized for the displacement that at low RPM, the engine ran terribly, stumbling and hesitating because there was not enough airflow velocity to atomize the fuel properly. But at race RPM, it was perfect, feeding the engine every molecule of oxygen it could possibly consume. When Herb finally bolted everything together and strapped the 427 to an engine dyno, the numbers were staggering: 595 horsepower at 7,200 RPM, 484 pound-feet of torque at 5,500. For 1968, these were numbers that belonged in prototype sports cars and drag racing, not stock car racing. The most powerful production car you could buy that year, the Corvette with the L88 427, was advertised at 430 horsepower, and everybody knew that was optimistic marketing. Building just one of these engines cost $12,000, which is $94,000 in today's money. Junior Johnson's team built 3 of them, plus 2 legal 350s for inspection duty. The total investment was over $40,1968, an amount that could have bought a nice house in Charlotte at the time. But money was not the real cost. The real cost was the risk, because once he decided to roll those dice, there was no backing out. The first actual attempt at a race day swap happened at Atlanta Motor Speedway in March 1968, and if you talk to anyone who was there, they will tell you the tension was so thick you could cut it with a hacksaw. Junior Johnson rolled through tech inspection at 2:47 in the afternoon. The inspector measured the bore, calculated the stroke, did the math, and slapped the approval sticker on the windshield. 357.8 cubic inches. Legal. The inspector made a note on his clipboard and waved Junior through. The car rolled into the team's assigned garage bay. The door came down, and that is when things got real. Herb Nab did not say a word. He just looked at his stopwatch and nodded. 12 men moved like they had rehearsed it 1,000 times, because they had. The battery cable came off first. Always disconnect the power before you touch anything else. Basic electrical safety. But also because a stray wrench hitting a live terminal can arc weld itself in place and ruin your whole day. Coolant drained into a catch pan, 4 gallons of greenish liquid that had to be disposed of carefully because leaving a puddle would raise questions. Fuel lines disconnected with those quick release fittings, the kind that snap apart with a quarter turn. Air cleaner assembly lifted off, exposing the dual carburetors underneath. Throttle linkage, 3 pins pulled, and the whole assembly swung free. Here is where it gets fascinating from an engineering standpoint. The exhaust headers separated at the slip joints with almost no effort. 2 spring clamps per side and the entire exhaust system dropped away from the engine. This meant the header stayed with the car, not the engine, which saved enormous amounts of time because you are not trying to maneuver an engine with 4 feet of awkward exhaust pipes hanging off it. The transmission connection, 4 bolts, came off in under a minute thanks to those alignment pins. The clutch linkage disconnected at a single pivot point. Radiator hoses, those dry brake connectors, push button release. Oil pressure line, same thing. The 2 massive electrical connectors on the firewall, one mechanic grabbed both, twisted the locking collars, and pulled them free. Motor mounts. This is where a lot of swaps would fall apart because getting an engine to lift cleanly out of a chassis requires everything to release at exactly the right moment. Herb had replaced the stock rubber motor mounts with solid aluminum units that bolted in place with 2 grade 8 bolts per side. Not 3, not 4, just 2 massive fasteners torqued to spec and then backed off 1 turn. When the time came, each bolt needed exactly 1 rotation to come free. 2 guys, 1 per side, synchronized like they were rowing a boat. Spin, spin, done. The lifting device, that rolling gantry with a chain hoist, was already positioned. The spreader bar hooked to the 4 lift points on the 350. 1 mechanic took position at the hoist, hand on the chain. Herb gave the signal, the chain went tight, the engine lifted, clearing the firewall by inches, clearing the steering linkage by less than that. This was not a slow, careful lift. This was smooth and deliberate, because slow means uncertain, and uncertain means mistakes. The engine came out, swung to the side, and lowered onto a reinforced rolling stand that was already positioned exactly where it needed to be. The 427 was waiting on an identical stand. It had been pre-warmed to operating temperature earlier in the day because dropping a cold engine into a car and then trying to fire it up immediately is a great way to crack a block or seize a bearing. The stand rolled into position, the spreader bar attached. Up it went, over the fender, into the engine bay. Here is what nobody tells you about engine installations. Gravity wants to help, but only if everything is perfectly aligned. If the motor mounts are off by even half an inch, the engine will not drop into place, and you will spend 10 minutes trying to muscle 600 pounds of iron into submission. Herb's preparation meant the engine settled into position like it was going home, because in a sense, it was. Those guide pins in the bell housing found their holes. The engine seated flush against the transmission. Motor mounts, 2 bolts per side, 1 turn each, torqued. Transmission bolts, 1 turn each. Clutch linkage reconnected. Exhaust sections slid together. Spring clamps snapped into place. Electrical connectors, twist and lock. Radiator hoses, push until you hear the click. Oil pressure line, same. Fuel lines, quarter turn. Coolant system filled from a pre-measured container so there was no guessing about volume. Battery reconnected. Throttle linkage, 3 pins back in place. Air cleaner assembly bolted down. Herb looked at a stopwatch. 38 minutes. 3 minutes under their target. But they were not done. 1 mechanic swept the floor, making sure there were no dropped bolts or forgotten tools. Another wiped down the engine bay, removing any fingerprints or smudges that might indicate recent work. The coolant drain pan disappeared into a storage cabinet. The 350, now sitting on its rolling stand, got covered with a tarp and pushed into a corner where it looked like any other piece of garage equipment. At 3:35, Junior fired up the engine, and this is where they made their first and almost fatal mistake. The sound was completely wrong. A 350 has a specific acoustic signature, a higher-pitched, faster rhythm because a smaller displacement and shorter stroke mean the engine cycles more quickly. A 427 sounds like distant thunder being amplified through a pipe organ. It is deeper, slower, more menacing. When Junior blipped the throttle during the warm-up lap, every crew chief in the garage area stopped what they were doing and turned their heads. That was not the sound of a 350. That was the sound of something much bigger and much angrier. Bobby Allison, who was racing that day, later said he knew something was different the moment Junior went past him on the track. The car was not just faster, it was pulling differently, accelerating harder out of corners, carrying more speed down the straights. The numbers did not match the equipment. But here's the thing about racing in 1968. Suspicion was common, proof was rare. NASCAR officials were definitely suspicious, but what were they going to do? Demand a teardown based on engine noise? Disqualify a car because it sounded too good? They had no evidence, no rule that had been demonstrably broken, just a nagging feeling that something was not right. Junior won that race by 3 full laps. In stock car racing, a 3-lap margin of victory is not just dominant, it is embarrassing for the competition. After the checkered flag, NASCAR did conduct an inspection, but it was basic: bore, stroke, displacement calculation. Here is where Herb's preparation paid off in a way that was almost artistic in its deviousness. He had machined special sleeves that could be inserted into the cylinders to reduce the bore measurement. These were not permanent, they were temporary inserts that fit snugly enough to give accurate measurements but could be removed in minutes once the inspection was over. With the sleeves in place, the engine measured 357.8 cubic inches, legal. The inspector wrote it down, signed off, and Junior's team loaded up and went home. They pulled off the same trick 4 more times that season: Charlotte in May, Darlington in June, Richmond in September, and most audaciously, Daytona for the Firecracker 400 in July, the same track where they had first conceived the plan. Each time, the swap executed flawlessly. Each time, Junior's car showed inexplicable speed, and each time competitors screamed foul, but NASCAR could not find anything concrete. Now, here is what most people do not understand about the other teams who tried to copy this system. Building the engines was not the hard part. Plenty of engine builders could assemble a 427 that made serious power. The hard part was the operational security, the logistics, the choreography, the ability to perform under pressure when one mistake meant career suicide. Buddy Baker's team tried it at Talladega in May of '68. They got the engine swap successfully, faster than Junior's team even, clocking in at 36 minutes. They were thrilled. They thought they had cracked the code. And then 3 hours later, a NASCAR official did a random spot check, something that happened occasionally just to keep teams honest. He looked at the inspection sticker, looked at his paperwork, and noticed that the serial number on the intake manifold did not match the number recorded during the original inspection. See, NASCAR had started recording serial numbers on major components, not consistently, but often enough that it was a risk. Buddy's team had not accounted for that. They had swapped the entire engine, including the intake manifold, and the numbers did not line up. The official asked Buddy's crew chief to explain the discrepancy. The crew chief, to his credit, did not crack immediately. He claimed it was a clerical error, that the inspector must have written down the wrong number. But when they pulled the intake manifold and checked the casting date, it was 3 weeks newer than the original part. Game over. Buddy was disqualified before he even made a qualifying lap. His crew chief was suspended for 6 months. The team owner was fined $30,000, an amount that nearly bankrupted the operation. The Wood brothers, who were always on the cutting edge of technology, developed an entirely different approach. Instead of swapping complete engines, they designed a system to change just the rotating assembly, the crankshaft, connecting rods, and pistons, while leaving the block in the car. This was exponentially more difficult from an engineering standpoint, but potentially faster and less detectable. Their method required removing the oil pan, which meant lifting the front of the car. They fabricated special jack plates that integrated into reinforced frame points, allowing them to raise the front end 18 inches in under 30 seconds. With the pan off, one mechanic would work from below, unbolting the connecting rod caps, while another worked from above, removing the cylinder heads. The pistons and rods came out the bottom. The crankshaft followed. Installation was the reverse, but with all the components pre-assembled into units. New crank with bearings already fitted and clearances checked. Pistons and rods assembled with rings installed and gaps properly oriented. Ring compressors ready to go. If everything went perfectly, they could swap the rotating assembly in 38 minutes. They attempted it twice. The first time at Charlotte in October '68, they succeeded. David Pearson won the race by 11 seconds, which does not sound like the dominant margin Junior had been posting, but 11 seconds in a short track race is huge. People noticed. The second attempt at Riverside in January '69 ended in catastrophic failure. Somewhere in the rush, a connecting rod bearing cap was not torqued properly. Nobody noticed during the installation. The engine fired up fine, ran fine during warm-up, seemed perfect. On lap 43, the number 3 rod bearing let go. The rod broke. The piston went through the side of the block like a grenade. 600-degree oil sprayed across the racing surface, turning turn 5 into an ice rink. 3 cars crashed in the resulting chaos. Pearson walked away uninjured, but the Wood brothers' reputation took a serious hit, and whispers started circulating about what they might have been doing. By 1969, NASCAR had seen enough. They could not prove what was happening, but they were not stupid. The new rules were comprehensive. Engines would be sealed after inspection using special tamper-evident paint that changed color if disturbed. Serial numbers would be recorded for blocks, heads, intake manifolds, even carburetors. Random post-race inspections became mandatory for the top 5 finishers, and those inspections would include detailed measurements and component verification. Cars would be impounded overnight in a secured area after inspection, meaning any work had to be done under official supervision. The era of the midnight engine swap in its original form was over, but the arms race did not stop. It just evolved. The new NASCAR security measures should have killed the whole operation, but racing teams are like water finding cracks in concrete. They always find a way through. Within weeks of the tamper-evident paint rollout, at least 3 teams had figured out how to beat it. The paint NASCAR used was a specialty formulation that changed from blue to red if the surface underneath moved or if the paint was disturbed. Seemed foolproof until a dentist who happened to be a racing fan mentioned to one crew chief that he used similar compounds for making molds of teeth. That casual conversation sparked an idea that was borderline genius. The process worked like this. Immediately after inspection, while the paint was still wet, a crew member would press a dental molding compound against it, the same silicone material dentists use to make impressions. This created a perfect negative of the paint's texture, including every microscopic detail. Once the engine swap was complete, they would apply fresh tamper-evident paint to the new bolts, then press the mold into it before it fully cured. The result was paint that looked identical to the original, with the same texture, the same pattern, the same everything. Unless an inspector was looking at it under a microscope, which they were not, it passed visual inspection perfectly. The serial number problem was trickier, but not insurmountable. Most engine components in that era had their serial numbers stamped into the metal, not cast into it. A skilled machinist could carefully grind away the original stamp, then restamp a different number in the exact same location using custom-made stamps. The new number would match whatever was on the inspection paperwork. The metal around the stamp would show signs of work if you looked closely, but who was looking closely at serial numbers on every single component? Inspectors were checking that numbers existed and that they matched the forms. They were not conducting forensic metallurgical analysis. One team, and nobody will say which one even now, went a step further and actually bribed a NASCAR official to provide them with genuine blank inspection seals. These were the official stickers with the NASCAR logo and holographic elements that were supposed to be impossible to forge. With access to blanks, the team could apply legitimate seals after their swap, and there was literally no way to detect the forgery because they were not forgeries. They were real seals, just applied at the wrong time. But the most incredible evolution of the cheating arms race came from Smokey Yunick. And if you know anything about racing history, you know that name means you are about to hear something absolutely insane. Smokey was a legendary mechanic and car builder who operated out of Daytona Beach. His philosophy on rules was famously simple. He believed the rulebook told you what you could not do, and everything else was fair game. When NASCAR said you could not run more than 358 cubic inches, Smokey heard that as a challenge, not a limitation. Smokey did not swap engines, he transformed them chemically. He had discovered through experimentation that certain chemical treatments could alter the molecular structure of aluminum cylinder sleeves, causing them to expand or contract in predictable ways. The treatment was temporary, with effects that lasted approximately 200 miles, which was perfect for sprint races that ran between 150 and 300 miles. During tech inspection, treated with one chemical formula, the cylinder sleeves would be contracted, and the engine would measure 358 cubic inches exactly. By race time, after the chemical reaction had progressed and the engine had come up to operating temperature, the sleeves would have expanded, and the actual displacement would be closer to 378 cubic inches. The beauty of Smokey's system was that it left virtually no physical evidence. There was no extra engine to hide, no swapped components with mismatched serial numbers, no disturbed paint seals. After the race, as the engine cooled and the chemicals dissipated naturally through heat cycles, the displacement would gradually return to its original measurement. If NASCAR tore down the engine immediately after the checkered flag, which they sometimes did, they would find the perfectly legal 358 cubic inch loader. The chemical residue was nearly undetectable unless you knew exactly what to look for and had access to laboratory equipment that did not exist at most racetracks. NASCAR suspected something was happening. Smokey's cars were consistently faster than they should have been, pulling harder on straightaways, carrying more speed through corners, but proving it was another matter entirely. They measured displacement multiple times. Always legal. They tore down engines looking for illegal components. Found nothing. They weighed cars, checked ride heights, inspected fuel systems. Everything was within spec. What they did not do, because it never occurred to them, was test for chemical treatments that could alter metal properties temporarily. That kind of thinking was a decade ahead of its time. In 1970, NASCAR changed their entire inspection protocol again. Now, engines would be sealed and inspected, then cars would be impounded overnight in a secured area with guards posted. Any work performed after inspection had to be done in full view of officials. This made traditional engine swaps essentially impossible, though one team allegedly managed to pull off a swap by staging a fake medical emergency that drew the guards away from their posts for 11 minutes. Nobody has ever confirmed if that story is true, but it has been told in enough garage areas over enough years that there's probably some truth buried in it. The overnight impound rule effectively ended the midnight swap era, but the impact of those few wild years rippled through racing in ways that are still visible today. Those quick disconnect fittings that Herb Nab pioneered, they became standard equipment in endurance racing. When a team needs to change an engine during the 24 hours of Le Mans, they are using technology that traces directly back to NASCAR teams trying to cheat in the 60s. The modular wiring harnesses with multi-pin connectors are now used in every form of professional motorsport, from Formula One to IndyCar to rally racing. Even the specialized lifting equipment and alignment systems evolved from tools developed for illegal engine swaps. But here's what really changed, and this is something most people miss. The sealed engine rules force teams to extract performance in entirely different ways. If you could not change displacement, you had to optimize everything else. Port design became a science. Teams started using flow benches to measure exactly how much air moved through intake and exhaust ports at different valve lifts. They discovered that bigger was not always better, that port velocity mattered as much as volume, that the shape of a combustion chamber could be tuned to create specific flame propagation patterns. This sounds technical because it is technical, but the practical result was that engines got more efficient, making more power from the same displacement. Valve train geometry became critical. The angle at which a rocker arm contacts a valve stem, the ratio between the two ends of the rocker, the spring pressure required to control valve float at high RPM. All of this was explored and optimized because teams could not just bolt on bigger parts anymore. They had to make the existing parts work better. The cam profiles became increasingly sophisticated. Instead of simple lope sheets, cam grinders started using mathematical models to create acceleration curves that open valves aggressively but smoothly, reducing stress on components while maximizing airflow. Friction reduction became an obsession. Teams started coating pistons with materials that reduced heat transfer and sliding friction. They began using different oil formulations, synthetic blends that maintained viscosity at extreme temperatures. They lightweighted everything that rotated because rotational mass robs power. Titanium valves, aluminum connecting rods, even magnesium engine components showed up as teams searched for every possible advantage within the rules. This technology did not stay in racing. It filtered down to production vehicles over the following decades. That variable valve timing system in your car, the one that adjusts cam timing based on RPM and load, exists because racing teams needed to make one camshaft profile work across a broader power band. The direct fuel injection that most modern cars use, where fuel sprays directly into the combustion chamber instead of the intake port, was refined in racing when teams were trying to extract maximum power from limited displacement. Even something as simple as low-friction piston rings, the seals that prevent combustion gases from escaping past the piston, were developed in racing and then adopted by automotive manufacturers looking to improve fuel economy. The human stories behind the midnight swaps are equally fascinating and often darker than the technical tales. Junior Johnson, who ran the most successful swap program, carried that secret to his grave in most ways. He would occasionally hint at it in interviews, usually with a sly smile and a comment about how creative teams had to be in the old days, but he never provided details. When pressed, he would just say that everyone was pushing boundaries and his team pushed a little harder. It was not until 2012, in an interview conducted just months before Herb Nab died, that the crew chief finally confirmed the whole operation in detail. Even then, he was careful about names, protecting mechanics who were still alive and might face consequences. Nab said something in that interview that stuck with a lot of people. "We were not proud of cheating, but we were proud of the execution." Does that make sense? We did something that should have been impossible. 12 men, 41 minutes, no mistakes, no evidence, nothing left behind. That took skill. That took dedication. Was it wrong? Probably, but it was also beautiful in its own way. The other mechanics who were involved have similar perspectives. Many went on to have long, successful careers in legitimate racing. They applied the skills learned during those midnight sessions, the ability to work under crushing pressure, the attention to detail where anything less than perfection means failure, the importance of preparation and practice. Several crew chiefs who worked in NASCAR during the 70s and 80s, during the sport's massive growth period, cut their teeth on engine swaps in the 60s. They learned that racing is not just about having the best equipment. It is about execution, about not making mistakes when everyone else is making mistakes, about finding edges that nobody else has thought to look for. One anonymous mechanic, now in his 80s, describes the psychological toll. Every single time we did a swap, I thought I was going to have a heart attack. My hands would shake so bad I could barely grip a wrench. We all knew what would happen if we got caught. Not just fired, blacklisted. You would never work in racing again. Every noise outside the garage made us freeze. Was that an inspector? Was that a competitor trying to spy on us? The paranoia was unreal. And then when it worked, when Junior won and we passed post-race inspection, the relief was incredible. We would all go out back and throw up from the stress, every single time. But the next race, we would do it again, because winning was worth it. The financial stakes were enormous. Teams that successfully pulled off swaps could earn an additional $50,000 to $100,000 per season in prize money, which in the late 60s was serious wealth. That could fund an entire operation for a year, pay for new equipment, hire better people, build faster cars. But the flip side was total financial ruin if you got caught. When Buddy Baker's team was disqualified and fined, the total cost between penalties, legal fees, and lost sponsorships was over $30,000. The crew chief never worked in NASCAR again. He ended up building street rods in a small shop in Tennessee, a talented man whose career was destroyed by one oversight, one serial number that did not match. But perhaps the most significant impact was on NASCAR itself as an organization. They learned the critical lesson that shapes how racing is governed even today. Racers will always push boundaries. Always. You can write rule books that are thousands of pages long, and someone will find a loophole in paragraph 3 of section 12. The solution is not just more rules. It is smarter enforcement, better technology, and the willingness to adapt. NASCAR started investing in better inspection equipment, in training officials to think like racers, in creating systems that made cheating harder but not impossible, because impossible is a challenge, and challenges invite innovation. The philosophy shifted from trying to eliminate all cheating to managing it within acceptable boundaries. Some innovations that started as rule violations were eventually legalized because they made racing better. Other violations were crushed hard with suspensions and fines because they created unfair advantages or safety risks. NASCAR became more sophisticated in understanding the difference between creative engineering and dangerous cheating. Today's NASCAR Cup Series engines are technological marvels that would make Herb Nab's jaw drop. They produce over 850 horsepower from 358 cubic inches, naturally aspirated, running on fuel that is essentially high-octane pump gas. That works out to 2.38 horsepower per cubic inch, a specific output that would have been considered physically impossible in 1968. These motors rev to 9,500 RPM all day long without failing. They run for entire races, sometimes 500 miles or more, with tolerances measured in 10,000ths of an inch. The combustion chambers are CNC machined so precisely that each cylinder produces identical power within a fraction of a percentage point. The valve springs are made from exotic alloys that did not exist 50 years ago. The oiling systems are dry sump designs with multiple scavenge pumps that ensure lubrication even when the car is pulling 3 Gs through a bank turn. But walk through the NASCAR garage area today and ask the older crew chiefs where all this technology came from, and they will tell you it traces back to those wild days when teams were hiding 427s behind closed doors. Every safeguard in the modern rulebook exists because someone found a way around the previous version. The inspections that now include laser scanning of engine components, that is because teams figured out how to hand port cylinder heads so subtly that visual inspection could not catch it. The fuel that NASCAR provides directly to teams from sealed containers, that is because people were adding exotic additives that were technically legal, but definitely against the spirit of the rules. The engines that are now built by a handful of certified manufacturers and sealed with electronic monitoring systems, that exists because the sanctioning body finally accepted that the only way to truly control what is under the hood is to control it from the moment of assembly. Look, the midnight engine swap era also fundamentally changed how we think about automotive performance and engineering constraints. Before the late 60s, the dominant philosophy in American racing was simple. Bigger is better. More cubic inches equals more power, period. Need to go faster? Build a bigger engine. Losing to the competition? Add displacement. This was the prevailing wisdom from the board tracks of the 20s through the muscle car era. But the sophistication required to execute these engine swaps successfully proved that engineering excellence could overcome displacement disadvantages in ways that went beyond just raw cubic inches. The lessons learned influenced engine development across multiple racing disciplines. Formula One in the 70s started exploring turbocharging as a way to extract massive power from small displacement engines. Those early turbo F1 motors were making over 500 horsepower from 1.5 liters, which is 91 cubic inches. That is more than 5 horsepower per cubic inch, numbers that seemed like science fiction to stock car teams. Rally racing went down a similar path, developing turbocharged four-cylinder engines that could produce Porsche-level power while weighing hundreds of pounds less. These developments were driven by regulations that limited displacement, forcing engineers to innovate in other directions, the exact same pressure that NASCAR's rules created. This philosophy eventually made its way into production vehicles. Consider the modern Ford EcoBoost engine as a perfect example. The 2.3-liter version produces 350 horsepower from about 140 cubic inches. That is 2.5 horsepower per cubic inch. And it achieves this while meeting strict emission standards and delivering reasonable fuel economy. 20 years ago, that combination of power and efficiency would have been impossible. The engineers who developed it stand on the shoulders of racing mechanics who proved there is more than one way to make power, that creativity and precision can overcome the limitations of displacement. The turbocharged engines in everything from economy cars to supercars today exist because racing proved that forced induction could extract performance that naturally aspirated engines could not match. The direct injection systems, the variable valve timing, the sophisticated engine management computers that monitor hundreds of parameters thousands of times per second, all of this technology has roots in racing's constant push to do more with less. Now, you might be thinking this is all ancient history, interesting stories from a bygone era that has no relevance to modern racing. But here's where it gets really interesting. Cheating has not gone away. It has just become more sophisticated, more technical, more difficult to detect. In the 2000s, NASCAR teams were caught using illegal engine mapping software that would pass inspection mode but switch to a more aggressive racing mode once the car hit the track. Others developed fuel systems that could temporarily hold extra capacity during qualifying, then return to legal volume for post-qualifying inspection. One team was caught with shock absorbers that changed damping rates based on temperature in ways that were not detectable on a shock dyno. The spirit of the midnight engine swap lives on every time a team finds a gray area in the rulebook and exploits it until NASCAR closes the loophole. It lives on in Formula One, where teams spend millions developing aerodynamic tricks that are technically legal but clearly against the intent of the regulations. It lives on in endurance racing, where teams push the boundaries of hybrid system energy recovery to gain tenths of a second per lap. The specific methods have evolved, but the underlying philosophy is identical. Find an advantage, any advantage, that the rules do not explicitly prohibit, and push it until someone makes you stop. What makes the engine swap era particularly special is the sheer audacity combined with mechanical elegance. These were not teams using exotic materials or computer simulations or wind tunnels. These were mechanics with hand tools performing an operation that should have been impossible under the time constraints, doing it flawlessly under immense pressure, and leaving no trace of evidence. That requires a level of skill and nerve that transcends the moral question of whether it was cheating. Think about the parallel to other famous moments of rule bending in sports. The 1919 Black Sox scandal in baseball, where players threw the World Series for money. That was pure corruption with no redeeming qualities. Lance Armstrong's doping in cycling. Same thing, cheating with nothing clever about it, just chemicals and deception. But something like the hidden ball trick in baseball, where an infielder pretends to throw the ball back to the pitcher, but actually keeps it to tag out an unsuspecting runner. That it's deceptive, technically against the spirit of sportsmanship, but executed properly, it is also brilliance and requires perfect timing and coordination. The midnight engine swap falls into that category. Wrong, yes, but executed with such precision that you almost have to respect the craftsmanship. The legacy of those years is complicated and contradictory. On one hand, these teams broke rules, risked the integrity of competition, and potentially endangered other drivers by running equipment that had not been properly inspected. Junior Johnson's 427 made his car significantly faster, which in close racing could have caused accidents if other drivers were not expecting that kind of acceleration. That is not a small thing. On the other hand, no accidents were ever attributed to the swapped engines, and the technology developed during that era advanced racing and automotive engineering in ways that benefited everyone eventually. There's also something to be said for the evolution of enforcement. NASCAR learned that simply writing stricter rules was not enough. They needed to think like the teams they were trying to regulate. This led to the development of the technical inspection processes used today, where officials are trained to look for specific types of violations based on what has been tried before. It's an arms race, and both sides have gotten substantially better at their jobs. Modern NASCAR inspections use templates to verify body shapes, laser scanners to measure engine components, and sealed electronic control units to prevent software manipulation. These systems exist because past generations of cheaters forced the sanctioning body to evolve. The story of the midnight engine swap is ultimately about human nature under pressure and constraint. When you tell someone they cannot do something, whether that is running a big block engine or going faster than a certain speed, a certain type of person hears that as a challenge. They start thinking about workarounds, about loopholes, about creative interpretations. This is not unique to racing. It happens in business and law and technology, anywhere there are rules and people trying to gain competitive advantages. The difference in racing is that the results are immediate and visible. You either win or you do not. The scoreboard does not lie. What Herb Nab and his crew accomplished in those 41-minute windows was a masterclass in preparation, execution, and risk management. They identified an opportunity that existed because of the gap between inspection and competition. They engineered a solution that required custom parts, specialized tools, and innovative techniques. They practiced until the operation became muscle memory, and they executed flawlessly under conditions where failure meant professional destruction. That is impressive regardless of whether you think it was ethical. Racing has always existed in that strange space between sport and engineering, between athletic competition and mechanical development. The midnight engine swap represents the purest expression of that duality. It was not just about having a faster car, it was about the ingenuity to create that faster car despite regulations designed to prevent it, and the skill to implement the solution without getting caught. That combination of creativity, technical ability, and nerve is what separates the legends from the also-rans. The next time you watch any form of motorsport, whether it is NASCAR, Formula One, IndyCar, or even local dirt track racing, remember that the teams you're watching are constantly probing for advantages. They are studying the rulebook, looking for ambiguities. They are testing parts that are technically legal but clearly pushing boundaries. They are thinking about ways to make their cars faster that the officials have not considered yet. This is not a flaw in racing. This is racing. It is the eternal chess match between competitors and regulators, between innovation and enforcement, between what is written in the rules and what is actually possible on the track. Those old engines from the swap era are gone now. Some are in museums, part of collections celebrating NASCAR's history. Others were destroyed decades ago, torn down for parts, or simply worn out and discarded. The mechanics are mostly retired or passed on, taking their stories and their secrets with them. The garages where these operations happened have been demolished or converted into storage facilities or body shops. The physical evidence has disappeared. But late at night, at vintage racing events, if you pay attention, you might see an old-timer walking through the paddock with a distant look in his eyes. He will stop at certain cars, run his hand along the hood, peer into the engine bay. He is not checking anything specific. He is remembering. Remembering when racing was wilder, when rules were more like suggestions, when 12 determined men could change history in 41 minutes with nothing but wrenches, nerve, and the absolute conviction that winning was worth any risk. That is the real legacy of the midnight engine swap. Not the cheating, not the controversy, but the reminder that human ingenuity combined with determination can accomplish things that seem impossible. That with enough preparation, skill, and courage, you can drop a 427 where a 350 used to be, race it to victory, pass post-race inspection, and drive away with nobody the wiser. At least for a little while. What is the most audacious piece of automotive engineering or racing deception you have ever heard of? Drop it in the comments below, because these stories deserve to be remembered. And if you enjoyed this deep dive into one of racing's most legendary chapters, make sure to subscribe to Legacy Motoring. We are just getting started with the untold stories of brilliant engineers who colored outside the lines and changed motorsport forever. Until next time, keep those engines running, keep pushing boundaries, and maybe, just maybe, check under your hood. You never know what someone might have swapped when nobody was watching.